Hello, everyone. Thank you for having me today. Can you hear my voice first? OK. So, and thanks to Muhammad and Rubam for inviting me. I'm actually not from Alberta. I am a PhD, fourth-year PhD student from the Technical University of Darmstadt in Germany. I am working in the Intelligent Autonomous System Lab. And inside it, we have also small groups. And my group is LiteRL. So we target like lightweight approaches for reinforcement learning. So in this talk, I will be talking about like a really big chunk of my PhD research that I have been doing for the last 3 years and a half, and I will shed light on the importance of using mixture of experts when tackling some of the real challenges that we face when doing multitask reinforcement learning. In addition, I will motivate why do we need to share modular and compositional knowledge between tasks. The ultimate goal of AGI is to have an agent that can solve multiple tasks, actually many. And in robotics, because I'm from a robot learning group, we want to design like an algorithm that trains a policy that can solve, that let the robot can solve actually multiple tasks, dealing with multiple objects and different skills. And the traditional formulation of reinforcement learning is not suitable really for this task. That's why like the common adaptation to the formulation of reinforcement learning is actually multitask reinforcement learning. And in this talk, I will be talking about some of the challenges that we face when dealing with the problem. And in addition, I will be presenting some solutions that will make us take really serious steps toward this goal. First, let's cover some fundamentals. I guess everyone knows this loop. Like we have an agent in the reinforcement learning, we have an agent and we have an environment. The agent interacts with the environment, generating some actions, and the environment feedback the agent with the next state and the reward signal. The objective in RL is to learn a policy by that can maximize the RL objective, and the RL objective is the expected sum of discounted reward signals. In deep reinforcement learning, we parameterize or approximate the policy by with a neural network with some parameter theta. And from now on, I will refer to the objective function when talking about the policy by J theta instead of J by theta for simplicity. In multitask reinforcement learning now, the environment is actually dealing with a batch of environments. So for example, like given some T tasks, the agent will generate some batch of actions and apply to the environments. And the environments will feedback the agent with a batch of next states and reward signals as well. Similar to reinforcement learning, our objective is to learn a single policy. And a single policy should perform all of these tasks under the condition of some context or like task information. And the objective that we are trying to maximize is actually the RL objective for each task under the expectation across all tasks. And the key aspect of multitask reinforcement learning is that learning a single policy can actually give us some sort of inductive bias to learn some common properties between tasks, and hence we can share them between different tasks, and hence accelerating the learning process. So the concept of sharing knowledge is like the core of multitask RL. And every approach tries to tackle this problem or look at this problem from different perspectives. In this talk, I will be talking using the perspective of looking at a batch of environments or a batch of tasks from the state space point of view. So assume now we have like a batch of video games or a collection of manipulation tasks. So in video games, for instance, each task is represented by, like the state of each task is represented by an image. And all tasks are represented by the same image in terms of dimensionality. However, the semantics of these pixels can differ from one task to the other. So I like to look at this problem as if there is actually a true state space, which is unknown. I don't know anything about it. But I know that each task actually lives in a subspace inside this true state space. And the idea now is that also this can also apply to manipulation when we deal with full state representation. So even if each task is represented by the state of each task is represented by a single vector, maybe each component of these vectors can differ in terms of semantics between one task to the other. For example, like opening the window, now the location of the window can be different from the semantics when looking at the button, because not even like the movement of this state component can differ from one task to the other. And the idea now is that, okay, I want to reconstruct this true state space, given the motivation that I want to capture the common properties between these tasks when looking at the state space. This can actually also be extended to action spaces. If you are familiar with multi-embodiment in robotics, when you have maybe like different humanoids with different limbs, this makes the action spaces actually different. When we want to do like multitask or like learn a single policy that can solve them all, we need to do some sort of padding. And now the padding will create the same semantic problem. So the concept, or like the important thing is to reconstruct this true state space will let us share this, learn these common properties, and hence share them among tasks. Theoretically speaking, when we look at the multitask reinforcement learning problem, we look at the contextual Markov decision process. And in this talk, I will be referring to the block variant, where we have a tuple of 5 elements. The first one is the context space. Second element is the true state space, action space, and a function that maps the context to some task-specific MDV components. For instance, for each task can have a different reward function, can different transition dynamics, and this subspace of the true state space that we are looking for. And now, since we already want to reconstruct this true state space, we said that the semantics can be different from one task to the other. And the idea now is actually to interpret from different perspectives these states that comes from different tasks, such that we can aggregate them and be able to actually share this sort of compositional knowledge between them. But how can we do this different interpretation? We use mixture of experts. So we use different models, and each model will look at the states agnostically to the tasks, and will try to interpret the state differently till we reconstruct this true state space. In the literature of multitask RL, this concept of mixture of experts has been already discussed. For instance, soft modularization is a method that proposed to learn blocks in terms of experts, and having a routing network that, given some task information and some state description, it can actually find different routes to encode this state, hence having different representation for each state. In the CARE paper, they introduced similar idea, but relies on the learning from language embeddings. So given a pre-trained language model, given some task instruction, you can encode it and use this embeddings to attend the representation generated from a mixture of state encoders. And now you have like some representation after the combination with the task embeddings, then you feed this to the policy algorithm and start learning. Lately also we have like PACU that looks at the problem from the parameter perspective. So it learns a set of abstract policies, and given some task information, you start interpolating this to generate task-specific policies. All of these approaches has like one common problem, which is there is no guarantee that all of the learned models are actually diverse enough. So the problem of diversity can actually affect our goal of reconstructing this true state space. If all of the experts simply collapse to a similar models, we cannot capture these independent components such that we can actually build this true state space. For this, for my first work, I introduced the idea of sharing orthogonal representations. And I refer now to the diverse representations from the orthogonality point of view. This work has been published at ICLR 2024 last year. And the title is Multitask Reinforcement Learning with Mixture of Orthogonal Experts. Going to the details of the approach. So I use the same formulation that I mentioned before, but changing one component, which is basically learning a phi function that maps each state to k orthonormal representations. And these representations will belong to a manifold called Stiefel manifold. And the Stiefel manifold is the manifold that contains all k orthonormal k vectors in the Euclidean space RD. So now I have a function. This function will map every state agnostic to the task to a point in this manifold. But how to approximate this like phi in practice, or like the phi function in practice? We approximate it using a mixture of experts. So we learn different models, and these different models will be like represented by neural networks with some parameter phi, and the expert should generate some diverse representations. And in our case, diverse means orthonormal representations. And now my multitask policy is formulated as two stages. The first stage is the representation side, where we generate this orthonormal representations. And the second part is like a function f that actually take this orthonormal representations and generate from it the actions that I need to use for the problem. And now I will modify slightly the multitask RL objective. So instead now of optimizing for parameter theta, I splitted the parameter into two parts, the representation part and the output part. And I need to satisfy some constraints that I want to make sure that those experts will generate this orthonormal representations. But how to satisfy this constraint? In our approach, we introduce an architectural choice called Moore, mixture of orthogonal experts. So the idea consists of three stages. The first stage is that we have mixture of experts, mixture of state encoders. Each will encode the state differently with different representation. And to ensure that those representations are actually orthonormal or like different, we use the Gram-Schmidt process. And I don't know if you are familiar with the Gram-Schmidt process. It's just a way to take some vectors and transfer it to, or like change it to the orthonormal version of it. And the application is simple. You take one vector and normalize it. Take the second one, project it to the orthogonal direction to the first one, and normalize it, and so on. So it's like a sequential process. Given now that we have some orthonormal representations that represent a single state coming from any task, the last stage is that given now a context or some task information, I will generate some weights, and this weight will combine or interpolate the representation that I have. Given the task-specific representation, I will use it to generate the actions that I have. The architecture itself can be applied to any RL algorithm. But in this talk, or like in this work, we were concerned about actor-critic algorithms. So we applied Moore, the algorithm, or the architecture choice, to PPO, an on-policy approach, and the SAC, or SAC, the off-policy approach. Also, the architecture can be used to model the critic network. But instead of encoding only the state, now we are actually encoding the state and action, and the output layer will just generate the Q value for this state and action combination. Now, let's talk about the evaluation of the algorithm and how it's actually effective. So I said, like, I will benchmark this approach on using two algorithms, PPO and SAC. First, we applied Moore on top of SAC, and we benchmark it on MetaWord, like a well-known and popular multitask RL benchmark. It has like some related but different manipulation tasks. It has two scenarios, dealing with 10 tasks or dealing with 50 tasks. And the state space is of a form of like a full state, so 39-dimensional state, and the action is 4-dimensional. Both of them are continuous. And in this work, we use a different or more challenging variant of MetaWord where we consider random goals. So now when we solve one task, we are actually solving tasks where the object in the scene can be located differently. Because before, in prior work, they use only fixed goal, and this task was actually easy. Evaluating more on MT10, we did like some benchmarking with some algorithms. First, we consider SAC, which is the single task variant or like the single task baseline, where we train using SAC on individual tasks, and then just take the mean across all of the performance metric. Second, we have MT-SAC, which is the adaptation of SAC to multitask RL by just simply concatenating some task information to the input. Then we have SAC plus film, where we use film module that induces some task information in every layer of the network. Then we have BCGrad, the gradient manipulation approach that tries to manipulate the gradients coming from different tasks to solve the task interference problem in multitask RL. And then we have three baselines, which are the one that I covered previously: soft modularization, care, and backbone. We reported the performance in terms of success rate during the course of training. As we can see, Moore managed to outperform all of the baselines at every single point of the evaluation. For instance, this is actually like a visualization of a one seed from Moore that managed to solve all the 10 tasks with 100% success rate. We also did an evaluation on MT50, where we are trying now to solve 50 tasks. We consider similar baselines. And one point to mention is that there was a typo in the paper, and some people actually recognized this. This is actually 100 million training steps. And as the final performance, we can see that Moore managed to outperform back then, like last year, it was like the state of the art was Baku, and it managed actually to outperform it. So this indicates, in general, that Moore is more sample efficient than the other methods. It has higher asymptotic performance, and lastly, it can actually handle large-scale multitask problems. Please. Experts. No, you just write experts. Because of the inductive bias. Inductive bias. So the concept of why we are doing multitask RL? To build like some sort of shared common knowledge, captured from different tasks, and then reusing this knowledge during training will accelerate the other tasks. When you look at each problem, like isolating all of the other tasks and look at each problem individually, you are actually not capturing any feature that can actually help you. In that case, you would have a smaller percentage. Can you please repeat your question? Yeah. Linearly dependent. Okay. This is then it's better because you find common knowledge and throw them away, get a smaller representation. That's why it's better and more efficient. This is the question. Okay. So the question, if I understood correctly, is that Gram-Schmidt process tries to learn minimal number of representations, right? The useless or like, okay. So if I understood the question right, Gram-Schmidt tries to take some linearly independent vectors, which could be in terms like linearly independent, but have correlated components, and then the Gram-Schmidt tries to produce some orthonormal representations by removing this correlated representation. And Gram-Schmidt is a differentiable process, so it's actually it creates some new path between networks, and this allows actually that the Gram-Schmidt will never have linearly dependent vectors. We saw this from the experimentation, that when you have Gram-Schmidt process, it's actually affecting the learning process. And this actually can open the question if we can remove Gram-Schmidt during inference or not, but yeah, I haven't done this. So I hope that this actually answered your question. Any more questions? Okay. So now, given that we looked at a problem where we have full state description and continuous actions, can we apply more to deal with visual observations in terms of images and discrete actions? To do so, we applied more on top of PPO. And we benchmarked it on mini-grid. It's a collection of navigation tasks. It has 3 scenarios, MT3, MT5, and MT7. Each is subset of the other. And the observation space now is actually an image of 7 times 7 times 3. And the action space is discrete of 7 components. When evaluating more on these 3 scenarios, first we considered the single task baseline in terms of training also PPO on all of the tasks and then average all performance. We consider also empty PPO, which is the adaptation of PPO to multitask. PC grad, we already mentioned it before, and MOE and more. MOE is basically the same architecture of more, but without the Gram-Schmidt process. So this is like testing if removing the Gram-Schmidt process is actually negatively affecting the performance. And it's not actually about the architecture that we design in terms of learning some experts and then doing the condition at the end, but rather it's actually from the Gram-Schmidt process. From the scenarios and from the results, we can see that more outperformed all of the baselines. And this can indicate that more can actually effectively deal with visual observations and discrete actions as well. Returning back to our constraint optimization problem, we said that we want to optimize for the multitask RL objective and satisfy some constraints. But why not just add this as a regularization term and not using Gram-Schmidt process? So we tested this, and we benchmarked more against this variant. And we found that more actually beat this baseline, which is basically minimizing cosine similarity loss on the representation level. And across all scenarios, we actually managed to have a better performance. And this actually indicates, and the reason for this is that the cosine similarity is actually conflicting with the main objective of the multitask RL problem. Because it's a regularization term, you need to keep weighting well the 2 objectives to manage to satisfy your goal. And it might be just requiring some tuning to have a better performance than what it has now. How about scaling the number of experts? So just to mention this, the number of experts are independent to the number of tasks. So the experts are actually being learned agnostic to the tasks. You are assuming that you want to generate some K orthonormal components. But what if we increase actually this number? Will we scale in terms of performance or not? And I think this is what nowadays like the story. What if we keep like scaling the number of parameters? Will we gain anything out of this? So we compared more to MOE. So same architecture, but without the Gram-Schmidt process. And we started from 2 experts, and we end up at 10 experts. From the results, on average, more actually increases in terms of performance. However, MOE saturates. Even like an example for this, the performance of more at 4 experts is actually similar to MOE at 10 experts. And this shows that we are actually making use of all of the experts and not actually collapsing to similar representations. Second, we wanted actually to understand if, like investigate if we can actually transfer some of the learned experts. So what if we train the experts on some source tasks, and then we transferred them in a frozen state to learn like some novel tasks? We did this by adapting Moore and MOE, and we trained on 3 tasks, and then we trained on some novel tasks, but keeping the experts frozen. And from the results, we can see that actually the transfer Moore matches Moore, which learns the novel task from scratch, which indicates that you can use also Moore for some sort of pre-training. So you can learn some experts. This can actually scale when you increase the number of source tasks, and then reuse the experts for learning some novel tasks by just training the output layer. So in the architecture, we haven't intentionally designed the role of each expert. So the learning process design or decide for the roles of each expert. But we wanted to investigate if we can actually understand anything out of this approach in terms of task relations, if Moore can actually capture task relations after training. So I already mentioned that we have some task-specific weights that combine the orthonormal representations that generates afterwards the actions. So if we took this vector, took all vectors, and we applied BCA, we can check if we can actually understand anything about the relations between tasks. So from the BCA, we can see that, for example, pick and place and big insert are actually closer to each other in the weight space. And this indicates that we can actually capture some task relations. So both of the tasks are actually reusing or using the experts similarly. So they are using them with similar weights. Also for drawer open and bottom press, and actually this was interesting because I couldn't imagine that those tasks are actually similar, but from the visualization, the two trajectories are more or less similar. But the intuition behind this, the reason for doing this interpretability study is actually just to see if we can capture any task relations. But the algorithm itself is not actually designed for any human interpretation of the expert's roles. So the takeaways from this work is that it's important to share diverse representations in multitask RL. Second, Grommer-Schmidt process is way better than doing just regularization and less maybe time consuming in terms of tuning and so on. More, it can be applied to any algorithm. We apply it to on policy and off policy. And finally, more outperform all of the baselines on two benchmarks, MetaWord, which is like large-scale manipulation tasks, and mini-grid navigation dealing with images and discrete actions. The more the experts, the more the performance, the higher the performance. For future work, I was inspired by the transfer learning experiment, and I thought maybe we can extend this to more advanced transfer learning approaches, or maybe to continual learning even. How will the performance change as we introduce more barrier environments? And this can actually, we saw this lately in locomotion using RL, using only PPO, and so many barrier environments, you can actually solve real-world experiments, real-world tasks. So I didn't have time to work on this, but the literature did. So lately, there was like an accepted paper. Lately, I mean like 10 days ago, accepted paper at TMLR that studied some plasticity matrix for multitask RL algorithms. So they applied gradual magnitude pruning to each of the multitask approaches to see if they can mitigate the plasticity issue in the multitask RL approaches. They have done this for all, showing some matrix. I will quickly summarize. Looking at more, doing this JMB, which is gradual magnitude pruning, actually negatively affecting the plasticity from these plots. And I would like to quote the authors. They say this is because of the representation orthogonalization, and more it's already exhibits some sort of stable plasticity, which can be a motivation to reuse this architecture for continual learning later. Second is the performance and barrier environments. So also, I didn't have time to work on this, but Viraj from UT Austin published a paper at RLC, which will be discussed a few days later, and benchmarked all of the multitask RL approaches on MetaWord variant on Isaac Gem, where you can now parallelize the environments. And he used on policy algorithm, PPO, and benchmarked all of these approaches. And looking at the performance of Moore there, the single head architecture, which is SH, Moore, is actually performing way worse than the multi-head variant. And this actually aligns with our results from the paper, because I didn't mention this, but in the paper we used multi-head architecture. So basically one output layer, single layer per task. And from the results on Meta MT10, it's producing reasonably well results, but on the MT50, it's actually beat all of the baselines. And this can indicate that with barrier environments, you can actually have better performance. So the limitation, as I mentioned, Moore is sensitive a bit regarding the output function that we use. So if you are using single head and you want to be more optimal, this will not work well, because we do this orthogonalization and diversity at the representation level, not at the output level. And that's why multi-head architecture is more appropriate for the approach. The Gram-Schmidt process is actually more, adds like an overhead because it's a sequential process. So you need to keep doing this orthogonalization each time step. And finally, during inference time, all experts should be activated. And this actually raises the next question, which is, how can we exploit only the experts during training? Okay, we saw from more that having more experts actually enhances the performance. But also it affects negatively the inference time, because now you will have a larger model, you need some higher memory requirements, and in robotics also, this having a larger model is not actually optimal, because this will reduce the frequency of generating actions and will make like this jerky movement in the robot, on the robot. So to tackle this, or to address this question, we address this question in our second work, in It's All Connected, Multitask Reinforcement Learning via Mode Connectivity. This has been recently accepted at the European Workshop in Reinforcement Learning, and it's under review in another venue. But before diving into how we actually addressed this question, or how we can actually solve the problem of inference time efficiency, I would like to define first what's actually mode connectivity. Anyone familiar with mode connectivity? No, okay. So mode connectivity is actually a phenomenon observed in deep learning, where we assume that if you trained a neural network 2 times, because of the stochasticity and because of starting from random positions, they will end up at different solution, and this is true. But in reality, 2 concurrent works in 2018, they discovered that the local minima are actually not isolated, but rather connected by simple nonlinear path, where the loss value is maintained low. And they managed to model this path by using maybe one-dimensional Bezier curve, or by using piecewise linear function. But this requires that you train 2 networks and then you start to connect them. Another work accepted at ICML 2021, they proposed to learn this subspace, or this path using a set of neural networks, and in a single run. Just a single run, you train or create this subspace, because you know it. You know already that there is some sort of connection between local minima. And they want to do this for having better performance for ensemble-based approaches and robustness to some label noise. But this is done just for supervised learning, not in reinforcement learning at all. And they created some subspaces, and they tried to learn some subspaces, for example, one-dimensional Bezier curve, a simplex, or a line. And for example, for the line, they parameterized this linear space with 2 neural networks, and then with some interpolation parameter, every training step, they sample a new alpha parameter, they combine, generate some new weight, and this weight will be on the line, do the backpropagation. Now you will, on average, you will reach to this high performance linear subspace. More importantly, they found also in the literature that it's not just about having curves that connects between local minima, but actually sometimes a linear subspace. And this happens when you share some optimization trajectories. So if you trained a neural network for X amount of epochs, and then you started from this final weight to do a bit more fine-tuning or resume training, the outcome from these 2 experiments will be linearly connected. So if you interpolated the weights, the performance on that line will be high. More importantly to us, or to my work, is this work published at ICML 2021, where they studied the relations now not between 2 local minima on a single task, but rather the relations between multitask and continual learning solutions. So they found that if you trained on task 1, for example, and then reached to the optimal solution, like suboptimal solution on task 1, and from there you started 1 continual learning step, or like experiment, or 1 multitask experiment. When looking at the outcome of all of these experiments, you find that there is actually a connection between the solution that solves task 1 and the multitask solution. So if you interpolated and computed the loss with respect to task 1, you see that you have actually constant performance without enforcing anything. This is just an observation. And also the same for task 2, the continual learning solution. So now the continual learning solution will be linearly connected to this multitask one. And they even did this like sequentially by increasing more and more tasks. Inspired from this observation, we know now that at least in deep supervised learning, that there is this kind of solution in the parameter space. And returning back to our question, how can we exploit the experts while having smaller model at inference time? We actually make use of this observation. And our hypothesis is that since it's already in supervised learning, it should be in reinforcement learning. So we target a solution where single task policies, now it's policies, are actually linearly connected to a common multitask one. And by that, we proposed actually more. STAR. STAR is an algorithm that tries to find this star topology solution where all of the single task policies are actually linearly connected to the center of the star, which is the multitask policy. So single task policies will act like experts. They will guide the training of the center of the star by maintaining this constraint of having constant performance along the lines. So if we maintain this high performance across each line, we are sure that now the performance of the center will have the same performance of all of the experts. Additionally, from our experimentation, we found that actually the center of the star, which is the multitask policy, has a positive effect on the experts. So because of the inductive bias, now the single task policies are not truly single task policies. They are trained only on one objective, but they are positively affected by the inductive bias induced here. Because we want just to satisfy this constraint that the performance across this line should be the same. And this will affect the expert as well as the multitask policy. Do you have any questions so far? No. Okay. It's the multitask policy. It's a parameter, yeah. Yes. Yes. So, I mean, it's a physical weight where when you interpolate this weight with each one and compute the corresponding objective function, you will have high performance. That's how it works. So it's actually a collection. For example, we have here 5 tasks. Then this solution contains 6 parameter vectors, 5 single task policies, and 1 the common, which is the center of the star. So you are interpolating the physical weights of the net. They are in different this weight space. How can, I mean, the performance? How can I make sure that the performance is like consistent on that? Yes, yes. Okay, so I mean, I quickly mentioned it in this slide where I was talking about creating a high performance linear space. So you parameterize a linear space with 2 networks. In our case, I will go now into the details, but I mean, in our case, we have multiple linear spaces, and all of them are actually connected at single weight. And during training, we sample like an interpolation parameter alpha, and we keep feeding this interpolated policy. And on average, if you keep feeding, like interpolating with random, using like a uniform distribution, you will end up forcing this solution to be in a good region. I will show you now. Yeah. Yes. I will tell you exactly how we do this with multitask. Yeah, I mean, the technicalities of this a bit more complicated than this one. So, but just returning back to our question, we wanted to make use of a like at the inference time to have lightweight model instead of relying on a mixture of experts, really complicated high-capacity solution. And now, given that now we want to satisfy all of these constraints, and given that the performance of the center of the star will be similar to the experts, we can simply, at inference time, use only the multitask weight. And we will have similar number of parameters as vanilla multitask array. So the outcome of our approach should be the following. Applying our approach to two tasks, for example, like door open and window open, the single task policies, which are theta1 in the parameter space, of course, theta1 and theta2, should be linearly connected to a common multitask policy, theta bar, where when we plot the objective with respect to each of these tasks, we can see that the interpolation will give us high performance region. And now we can simply use only the multitask weight and throw away all of the experts. But before going into the details of how we actually learn this, we need to have a metric that defines mode connectivity. We adopted a metric from the literature of mode connectivity in supervised learning, and we adapted to reinforcement learning. And this metric is called performance barrier height. It states the following. The performance at the endpoints, in our case, it's the multitask and the single task performance. The average should be, actually, there's a typo. This should be a plus, not a comma. So the average performance should be similar to the worst performing policy on the line. By satisfying this condition, we are sure now that we have consistent performance. That's our criterion to know that if we have mode connectivity or not. And now the objective function is the following. We are optimizing for a collection of solutions. Given T tasks, we are actually optimizing for T plus 1 solutions, the single task policies and the multitask policy. And we want to maximize the objective with respect to the endpoints, the theta C for any task, and the theta bar, which is the common one. And here, now we are doing this trick. So we are optimizing the endpoints while satisfying some set of constraints. And the constraints are formulated using the above metric. Did you get now how we do it? So we are optimizing the endpoints. So optimizing the single task policy and the multitask policy, and make sure that we have mode connectivity using this constraint. Hmm? Like here? Okay. So this metric is the metric that we use to identify if we have mode connectivity or not. If we have simply consistent performance on the linear space. Okay? And the objective now is to optimize for this collection of solutions. T single task policies and 1 multitask policy. The objective is the following. We know that from multitask RL objective, we want to optimize for the RL objective for each task, and then do the expectation of all tasks. But now we have multiple solutions. To ensure that we are maximizing the performance of the endpoints, because this the one that actually controls the definition of mode connectivity, we optimize for the single task weight and the multitask weight simultaneously, while satisfying this constraint. I haven't still discussed how we actually satisfy this constraint. For now, this is the constraint problem that we want to solve. Is that clear now? Okay, now how can we actually do this in practice? Similar to Moore, we wanted also to apply this to actor-critic approaches. And for this, we wanted to do some relaxation for the previous constraint optimization problem. And we did so by, for the policy update step, we now calculate the loss function of the actor with respect to the single task, as if we are doing single task RL. And also with respect to the core, or like the center of the star, which is the multitask policy. And then to satisfy this constraint of mode connectivity, we have this item where we actually, every time step, we sample an interpolation parameter, alpha, and we compute the loss function with respect to this interpolated policy in the parameter space. And after computing the loss, you will back propagate now the gradients to the endpoints, and this will force the endpoints to reach in a region where you have actually good performance on the line. Because you are actually telling the network during optimization, I want this optimization interpolated point on the line to have also good performance. This is how we satisfy the constraint that we have. For the critic mode, go on, please. We can have fixed alphas, but this will be computationally limiting a bit. What do you mean by not having? Why do we need to have? Yeah, it should be with random, like a random variable. Okay. Okay. So this loss computation is done for each task. So I mean, I mentioned earlier that we have this star shape. So I want to do this optimization for each task separately. And to optimize now, let's use the pointer. And now to optimize for the policies on each line, I will sample an interpolation parameter and compute the loss, back propagate, and this will affect the center of the star as well as the single task policy. And I do this for all tasks. In actor critic, we need to model the value function or the Q function. So for that, we learn critic model for each task. Basically, for each arm of this star, we have a critic model, and we do similar thing. But now instead of interpolating the parameter, we are just conditioning the model on the alpha parameter, just to tell the network, the critic network, that you are now modeling the Q function of this specific interpolated policy. So we also optimize this by computing the loss with respect to the single task, multitask where alpha equals 0, and also when alpha is basically random. Two key components in our approach is actually that we share data between the policies on each line. We do so by sampling at each, for exploration, at each step, at each episode, we sample one interpolated policy from the line. We do exploration by generating a rollout and save this rollout in the replay buffer for each task. And now all policies are actually learned from this shared replay buffer. And this actually helps us in terms of performance. Second, we have one critic per line. And this is actually really effective and let us actually model the critic value quite efficiently. When we apply star to a collection of tasks from Mojoku, like 4 tasks, we can see that we actually managed to find this star shape for 4 tasks. So the center is the multitask policy, and the endpoints of the star is the single task policies. As you go on each line, you will have consistent performance. And looking at the performance of the endpoints, you can see that we are solving all tasks. And by looking at the center, we are also solving all tasks. And this motivates the idea of throwing away the experts at inference time and just using this compact solution in the middle of the star. We did also this for MT10 from MetaWorld. So now we managed to actually scale the approach to a larger number of tasks. During training, it was actually interesting to see how this star is actually formed. So it's actually gradually satisfying constraints until we end up at the solution where all linear path has like good performance. But when it comes to practice, learning for T tasks will require now T+1 models, and this is not practical at all. For this, we propose to cluster tasks into groups and learn one group-specific policy for each group, and try now to enforce this connectivity between each group-specific policy and the center of the star. So same concept, same motivation, but now we have less number of experts, and now we are actually comparable in terms of number of parameters to the other MOE approaches. So we used in this work like 3 ways. either naive clustering, simply using the order of the task ID and keep like clustering them, or basically random. Each seed you assign randomly the tasks, or doing manual work by having some prior knowledge and then do the clustering. And this is an example of a manual cluster that we did on MT10 from MetaWorld. Now we will evaluate this practical variant on Mojoko, and we compare also to Moore and MOE. And on average, when looking at the performance on all tasks, our approach can actually beat all of the other baselines while only using the center of the star. So now we have really simple model with the same number of parameters at inference time as MTSAC, for example, but still outperform all tasks or baselines. We did also another interesting thing, which is how about scaling the number of experts for training and looking at also the number of experts at test time. So for Moore, or the other MOE approach, as you increase the number of experts, you will also increase the model size at inference time. However, for star, you will still keep the same number of parameters at test time because you will just increase the experts, but the center will be the same. We evaluated also on MetaWorld, MT10 and MT50. From the results, we can see that we have a lower actually performance than Moore. However, in terms of the inference time efficiency, in terms of the number of parameters, we have 4x reduction in the number of parameters. Actually, now the number of parameters is similar to MTSAC, and the performance is way higher, like 15% higher. Same for MetaWorld, MetaWorld MT50. And this actually indicates that star can find like a trade-off solution between performance and test time efficiency. But how about like just distilling the knowledge instead of relying on mode connectivity? Are you familiar with the concept of distillation? So now we have experts. Instead of relying on this mode connectivity constraint, you will just use distillation. So we did so by removing the mode connectivity term and use instead minimization of KL divergence between policies. So from the experts, you distill the knowledge to the center of the star, or like the expert. When we compare our approach, we outperform the distillation. And the reason for this is that distillation is not designed to be online. Our experts are actually simultaneously learned with the multitask policy. But in the traditional formulation of student-teacher approach in distillation, you train first the experts, and then you distill. And this will increase the training time. What if we go beyond actually the multitask policy? What if we reuse other policies from the star topology? In case we have resources, how can we make use of this? We applied on Mojoko and MetaWorld. We benchmarked the group-specific policies, which are the experts, and the midpoint of each linear space, the multitask, and max online. And max online is basically trying different interpreted policies and taking the best one after computing the metric. Of course, it's clear that max online is performing the best. However, multitask is not that away from the max performance on the line. Inspired from some works in RL that studied the robustness property of learning a subspace of policies, but in the single task case, we also did the same test. So in this work published at iClear 2022, they learn a subspace of policies, and this will capture different behaviors. And at test time, you can change slightly the environment by maybe like increasing the length of a half sheeta, or maybe removing one of the legs. But still, you can find a solution from the subspace that can actually solve this changes, or like slight change in the environment. Since we have also linear spaces for each task, or like for each group, we wanted to see if we can preserve this. So we trained star on a nominal value, like nominal tasks with nominal mass and friction values. We scaled the mass and the friction during inference time. And from the heat map, we evaluated multiple points on the line, considering the multitask policy and the single task policy with respect to different scaling factors for the mass and also for the friction. We can see from the plot that selecting maybe the multitask policy is more efficient in the case of half sheet and mass. And also in the friction, it's better to use maybe models on the single task side. or like the group specific side. When comparing also to other baselines that doesn't build this subspace, so they don't have the advantage of selecting one of a good solution for this variant of the problem, our approach outperformed all of the baselines, including more. And this indicates that star can actually preserve the same robustness property at inference time. I will wrap up. So the takeaways from this work is that we empirically proved that there is a solution where single task policies are actually linearly connected to multitask ones. Star helps us to exploit the experts only during training and use the center of the policy at the center of the star at test time, so becoming more efficient. We also discussed some other things that we can get out of the star, like different inference strategies or robustness property. A limitation is that we need some prior knowledge to create the clusters. Of course, we have other approaches to cluster, but most of the results are reported with manual clustering. This can open the door for maybe learning-based clustering approach. When will this hypothesis will fail? We didn't really focus in this work on finding corner cases where this observation actually fails. But in reality, all of the experiments that we have done showed that we can find connectivity between all single task policies and multitask. We want also to apply star to on-policy approaches. To conclude, we represented more, which is a representation learning perspective approach. Sharing diverse representation is essential in multitask RL. In star, we looked at the parameter perspective, and then we exploited the experts during training and learned a better compact multitask policy. For the future of multitask, I would say all of the works has been overfitted maybe to focus more on specific benchmarks, including MetaWorld. We need to change this. We need to move to other benchmarks or maybe real-world experiments in robotics. Maybe using different architectures like transformer or diffusion models. Like lately, there is this vision language action models in robotics. Maybe we can use multitask RL to fine-tune these big models or breed-in them in online or offline setting. Also, it's important to focus on the critic design because we found lately from the literature that designing a better critic will actually positively affecting the multitask performance. By this, I would like to thank all my collaborators and advisors. A bit of advertisement. I am organizing a workshop at RLC next week. We will have an excellent line of speakers, including Marlos. I think you know him. And I would like to see you all there. By this, thank you for listening.